Oftentimes when we have a differential equation, the thing that we're really interested in is the long-term behavior of the solutions. So for example, what is the eventual speed of a falling object? Or could be, what is the eventual concentration of salt in a tank of water some time in the future? And so these kind of questions are essentially questions about limits of solutions to differential equations. And the main point I want to convey in this lecture is that it's often not necessary to actually solve the differential equation in order to glean this kind of information. And that's what we're going to talk about today. And so equilibrium analysis is actually a really powerful method to understand the long-term behavior of solutions to autonomous differential equations. And I don't recall whether I defined that in an earlier lecture, so I'm going to start by saying what I mean by autonomous. So basically for this lecture and next lecture, we're only going to be talking about autonomous differential equations. And so a first order differential equation. We're going to call it autonomous. So it's called autonomous if if it has a form. So I need to be able to write it in the following way. I want to be able to write it as dy dt. So here, y is my dependent variable, t is my independent variable. And then on this side, I only want the dependent variable to appear. So in other words, I can write this as some function of the dependent variable alone. So in particular, there should be no occurrence of t on this side, no occurrence of the independent variable. No occurrence of t over here. Okay, and we've seen a lot of these. In fact, this is probably the main kind of differential equation we've seen so far. And so I just want to say a few words about, what does this really mean to be autonomous? So I guess I told you mathematically what it means, but physically, what does this mean? So the way to think about this is that a differential equation is autonomous if the underlying mechanism of the physical process. So the mechanism of the physical process, it doesn't change with time. Okay. So at least the mechanism is the same, no matter whether we look at it, on a Monday or a Saturday. And so, one example of an autonomous process might be a pollutant draining into a lake. This is like an example we saw in a recent lecture. So a pollutant draining into a lake. Let's say it's just draining into a lake at a constant rate. Well, that would be an autonomous process. And so if I look at this tomorrow rather than today, there might be more or less pollutant in the lake, depending on, how much is flowing in, how much is flowing out. But the point is, the mechanism of this process doesn't change. Okay, so what would be a non-autonomous process? So I'm just going to write the same thing. So pollutant draining into a lake. But let's say the leak is getting worse with time. Okay, with time. So this is actually exactly the example from the lecture. So this would be a non-autonomous process. Okay, because if I look at it tomorrow, well, then the differential equation is going to be a little different, right? Because I have to account for the leak getting worse. So the mechanism of the process has actually changed a little bit. Okay, so that's autonomous versus non-autonomous physical processes and autonomous differential equations. I just want to stress, the solution to this differential equation will definitely involve t. I mean, sort of by definition, right? We're solving for a function y of t. So we're talking about the differential equation itself, right? If we can write the differential equation itself with no occurrence of t, then it's autonomous. Okay. So the main fact about autonomous differential equations is that they're all separable. So all autonomous, well, not necessarily the main fact, but certainly a very useful one. So they're all separable. That doesn't necessarily mean we always want to solve it by separation of variables. This f of y might be a very complicated function, and we end up having to integrate. Yeah, so how would we actually separate it? Well, we should say that, right? You divide by this function here to get 1 over f of y times dy dt equals 1, and that's separating the variables. So they're all separable. But this 1 over f of y, we're going to have to take the integral of that, and that might be a very difficult integral to actually do. So we're going to look at an alternative way to think about equations like this today. Okay. So actually, before I talk about equilibrium solutions, I want to just mention one other thing. So what is a direction field? What does a direction field of an autonomous differential equation look like? The direction field of an autonomous differential equation. Well, I'll just draw an example of one. Okay. So let me do that over here. Okay. So let's say at this point right here, and as usual, we'll have a t over here, and we'll have y here. So let's say at this point right here, we calculate that slope. Okay. Well, what are we going to calculate at this point here? We already know the answer, right? Because the differential equation doesn't depend on t. So no matter where I am on the t-axis, as long as I'm at the same value of y here, I'm actually going to get the same slope, right? Because I'm actually just plugging in y to my the y coordinate to my differential equation in order to calculate the slope of these line segments. So these are all just going to look like that one. Okay. And similarly, if I have a slope like this down here maybe, then along this horizontal, this invisible horizontal line, they're all going to look like this. Okay. So let me just sum it up in words. So the line segments along any horizontal line have the same slope. Okay. So that's how you recognize the direction field of an autonomous differential equation. Okay. So that's enough about that. So why are we actually studying autonomous differential equations? That's so we can talk about their equilibrium solutions. Equilibrium solutions. This will be the main topic of today's and lecture and the next lecture. Equilibrium solutions. Okay. Let's underline that. So what is an equilibrium solution? A solution of the form. Okay, we use the same dependent and independent variable. So of the form y of t equals a constant is called an equilibrium solution. Okay, so simple concept. Simple concept, but turns out to be very, very powerful. So first thing we should do is talk about how do you find equilibrium solutions. So to find equilibrium solutions, well, let's think about it. Okay, let's see if we can deduce it. So equilibrium solutions are constant solutions. Well, what is the derivative of a constant? A derivative of a constant is just zero, right? So if we have an equilibrium solution, we should be getting zero, the zero function on this side over here, right? So that basically tells us how we can find it, find these equilibrium solutions. What do? We set the dy dt to 0. And then we have to find the constant solutions, right? The constant values of y that can satisfy the differential equation. So we set dy dt equals 0 and then solve for y. And solve for y, okay? Okay, so let's do an example really quick. So example, I'm actually going to take one from an earlier lecture. So this is the water tank problem from lecture 2. Water tank problem from lecture 2. Okay. And just to kind of recall what that problem was about, we had a water tank. Okay. Kind of like this, and we had a pipe leading in, and okay, and then we had another pipe over here leading out, and it was full of water. Okay, and then the water's coming out, and so the water was actually coming into the tank at 2 liters per minute. Oh, and it was a 100-liter tank, by the way. And water was coming out of the tank at the same rate. And then the incoming water was actually, it had 5 grams per liter of salt dissolved into it. Okay. And we wanted to understand S of t, which was the amount of salt. Okay, in grams. Okay, great. So let's just recall what the differential equation ended up being. I'll kind of walk us through this again. It's always good to practice these kind of problems. So we have the rate in of the salt minus the rate out of the salt. That's going to be what the rate of change of the salt is going. What's going to affect the rate of change of the salt. So how much salt per minute is coming in? Well, it'll be 2 liters per minute of water times 5 grams per liter, which is the concentration. So it'll be 10 minus how much salt is coming out. Well, how much salt is in 1 liter is S. S is the amount of salt in the entire tank divided by 100. And then we have to multiply by 2. So we actually end up with S over 50. So there's our differential equation. Okay. What are the equilibrium solutions? Okay. So in other words, is there some amount of salt that I can have in a tank such that, if I continue this process, the amount of salt in the tank will always just remain constant. So the amount coming in will exactly cancel out the amount coming out. And it turns out there is such an amount. And to find that, we set ds dt to 0. We get this. S over 50. And then we solve for S. Okay. So S over 50 is 10, which means S is 500 grams of salt. Okay. And so what do we just say? Well, we said that S of t equals 500. So the constant function 500. Well, this is a solution. So it's in particular, it's an equilibrium solution. It's just our name for constant solutions to the differential equation. Okay. And so if we start with 500 grams of salt in a tank, then it turns out that's the right amount of salt to have so that the outgoing rate will exactly cancel out the ingoing rate. Right? Okay. But, okay, so that's not so impressive. You might have been able to figure that out just by sort of deducing that, oh, we need 5 grams per liter coming out. Right, so we need there to be 500 grams of liter in the tank because there are 100 liters. Okay, so maybe that's not so impressive. But the impressive thing is that equilibrium solutions actually allow us to deduce the behavior of all the other solutions, even the weirder ones. So I want to show you how that works. So let me grab a new page. Okay. So let me copy down the differential equation again. ds dt is 10 minus s over 50. Okay. Now, here is what I would like to do. So I'm gonna actually draw a little graph over here. Okay, so here's t and here is s. And let's actually go ahead and graph our equilibrium solution. It's just going to be a constant solution, right? So the solution will just look like a horizontal line, right? And it's just a constant function 500. Okay. Now, that equilibrium solution, what it essentially does is it partitions this plot into 2 regions. So we can either have s less than 500, or we can have s greater than 500. Okay. So here's what I'm going to look at. So let's say we'll say s of 0 is starting out less than 500. So we're down here somewhere. Okay. We have less than 500 grams of salt already dissolved in the tank. Well, then what can we say about ds dt? Okay. ds dt, so imagine s we have is some number less than 500. Well, then s over 50 is going to be less than 10. Right? And then 10 minus a number less than 10, that's going to be positive. So ds dt is going to be positive. It'll be greater than 0. And what does that mean in terms of s of t? Well, if you remember from calculus, if the derivative is positive, what does that mean about the function? It means s of t is increasing. Okay? So maybe I'll draw like a red arrow here. So if we start out anywhere down here, we are going to be increasing. Okay? And then let's do the other case really quick. So what if we start out greater than 500? So if we have more than this amount of salt. Well then, similarly, if s is greater than 500, this number here is going to be greater than 10, and then we end up with a negative number here. Right? So ds dt is going to be less than 0. And so s of t is decreasing. So basically, any solution that starts up here is going to be decreasing, and it will actually decrease down toward the equilibrium. And so let's plot a few solutions. So I mean, let's say I start at 0 even. What's going to happen eventually? I don't know exactly what it's going to look like, but I'm going to be increasing. I'll continue increasing until I get to the equilibrium. I'll never actually touch that equilibrium, turns out, but I will asymptotically approach it. Okay, so I'm just sketching a few solutions. That's what I'm doing here. This is what I mean. You can really determine the behavior of all the solutions just from figuring out these equilibrium solutions, and those allow you to partition the s-axis here into different regions. In this case, 2 regions. I'm sketching some more solutions. So this is what all the solutions are going to look like. Okay. And so in particular, in this case at least, for any solution, okay, s of t, we have that, what do we have? The limit of that solution as t goes to infinity is going to be what? Well, it's going to be 500. Okay. And really quick, I just want to justify why it really has to approach this equilibrium solution. So if you pick any line here, right? So like let's say I pick this horizontal line that's a little bit less. Okay. Well then, if I plug in whatever that s value is, right? Then this will end up being something that's not 0. It will be something positive, actually. And so I'll get some, in the direction field, I'll get these line segments. They're telling me that my solution will need to be increasing. It will need to be increasing toward this equilibrium. And actually, in this case, if we go below here, we'll be increasing even more steeply. And you can see that from the equation. And so even if the slope is very gradual here, we actually know that any solution here will, given enough time, it will cross this dotted line here. And because this argument works for any dotted line we want, arbitrarily close to this blue line, we can actually prove that any solution starting down here will eventually approach this equilibrium solution asymptotically. So that's just a quick argument for why they actually have to approach it. Okay. So I want to do another example, but before I do, I want to tell you a word for this kind of solution. So this kind of solution is actually called this is called a stable equilibrium. It's called a stable equilibrium because nearby solutions are approaching it rather than diverging away from it. Okay. So there are actually 3 kinds. I think there are only 2 kinds, but there are 3 kinds of equilibrium solutions. So the 3 kinds are stable, unstable. Okay, you can probably imagine what that's going to look like. And the 3rd kind is called semi-stable. And just in words, so stable equilibrium solutions attract. So a stable equilibrium solution attracts nearby solutions. And an unstable equilibrium repels nearby solutions. And a semi-stable actually it does both, let's say. So what do I mean does both? How can I do both? The easiest way to explain this is with pictures. So let me quickly sketch some pictures of these 3 situations. Okay. So I will draw my equilibrium solutions. So these are my equilibrium solutions in each case. So here's what a stable equilibrium looks like. We actually already had one above. But solutions starting nearby, they'll converge toward the equilibrium like this. Unstable, solutions that start nearby will actually diverge away like this. So this is what an unstable equilibrium looks like. Then semi-stable, so the way it works is on one side of the equilibrium, I might be diverging away like this, okay? I can't be doing both on one side, but on one side I'm diverging away, and then on the other side I'm actually converging to the equilibrium. Okay. And so I could have drawn it the other way, right? So I'll say or vice versa. It could have been converging at the top and then diverging down here. That's what a semi-stable equilibrium is going to look like. And so let's practice with this concept. So let's do an example. In fact, yeah, this will be an example of how to apply these 3 kinds of equilibrium solutions. So let's consider a solution to the following differential equation, dy dt equals, it's going to be a complicated looking one, 4 minus y times y minus 1 squared. Okay, so that's my differential equation. Okay, and I'll tell you an initial condition. So let's say a solution with y of 0 equal to, let's do 3. Okay, y of 0 equal to 3. And I want to know what is the eventual behavior of this solution. In other words, what is the limit of y of t as t approaches infinity? Okay. Okay, so your first thought might be to solve this differential equation. After all autonomous differential equations are separable. This is an autonomous differential equation, right? We don't see the variable t over here. So we can separate variables by dividing by this entire expression. However, that means we'll have to take the integral of 1 over this thing here. And that's not the easiest integral in the world. It'll involve partial fractions. And so we'd like to avoid that if possible. And it turns out we can. So the idea to solve this problem without having to analytically find a solution to this differential equation is to first find and classify. So we want to understand the nearby behavior. So we want to find and classify the equilibrium solutions. Okay. All right, so let's go ahead and do that. How do I find the equilibrium solutions? I set dy dt equal to 0. And then what do? Well, I have to solve for y. And that will tell me what the constant functions are that satisfy this differential equation. Okay, so I'm sure you can see what they are. Y could be 4, right? Or y could be 1. Okay. Technically, this is a double root, right? So 1 is a double root to this factor here, but that doesn't matter. It only gives me this one solution, this one constant solution. Okay. And so I'm going to start drawing a picture down here. Start over here. Okay. Okay, so this will be my my t-axis, and this will be my y-axis. Let's go ahead and plot the equilibrium solutions. So I have one here, and then I have one here. So those are my equilibrium solutions. Okay. So this one is y equals 1, and this is y equals 4. And these really are solutions to this differential equation, right? If you plug this in and you plug in its derivative, you get a true statement. That's the whole idea of this method of plugging in 0. Okay. Let's classify these equilibrium solutions. Okay. So we actually have 3 regions to consider here. We have this region up here. So we have y greater than 4. And we have y between 1 and 4. And we have y less than 1. So those are our 3 regions to consider. Let me actually make a little table here. Okay. Okay, so here are 3 regions. And I want to understand what's happening in each region. So we're going to do this just like the other example. Okay, so first of all, I'm just going to copy this out again. 4 minus y, and then y minus 1 squared. Let's make this a column. Okay. So let's say y is greater than 4. So we're starting up here with some value greater than 4. It could be an initial value, it could be a value out here, it doesn't matter. We're greater than 4. What can we say about this? All right. So we actually have to go through and say, Well, if y is greater than 4, let me do this in red maybe. So see, 4 minus y will then be a negative number. So I'm just going to draw a minus sign. This will be a negative number. And y minus 1 squared, that will be a positive number. And so what about their product? Right? So what about dy dt? Right? This is dy dt. Well, a negative times a positive is a negative. So dy dt is negative. And so what does that mean about y of t? Y of t is going to be decreasing. So my solutions that start above 4 will be decreasing toward this equilibrium here. Such a powerful concept. Any solution up here is going to be decreasing to this equilibrium. Okay, what if I start between 1 and 4? So actually, yeah, let me draw a little red arrow there just to signify what my solutions will look like. Okay, what if I start between 1 and 4? Now this first factor is going to be positive, right? I have 4 minus a number less than 4. And the second factor, well, that's a square. So isn't that always going to be positive, right? Even in this case down here, the square of a negative is still a positive. So that's always going to be positive. Let's just fill this one in too. 4 minus a number less than 1, that's still positive. So positive times a positive is a positive. See, because we're multiplying them together in the differential equation. And positive times positive is a positive. So in these two cases, we will be increasing. Okay. So let's draw that here and here. Okay. And now for the fun part, we can start sketching in all the solutions. So if I start down here, what's going to happen? I'm going to come up and approach this equilibrium, right? Because at this equilibrium, I need to be moving this way, right? My slope is going to be 0 along the equilibrium. So I can't actually cross the equilibrium, but I am going to approach it. Okay. I'll draw another one in there. What about up here? Same kind of thing's going to happen. So if I start here, I'm actually going to approach this equilibrium. If I start down here, I'm going to also approach this equilibrium, maybe a little slowly, more slowly. Right? Even if I start really close to this one, maybe I'm so close I'm also going almost horizontal, but all solutions in this region will increase, right? So I will eventually increase. And where will I increase to? I will increase to this equilibrium, y equals 4. Okay. What if I start above, right? If I start here, so this is our equilibrium analysis over here. And what that determined is we will be decreasing. So our solution will be decreasing, and it will not be able to cross this equilibrium, right? But it will converge to the equilibrium. And same with the solution starting up here. And the same with the solution starting all the way up at 1,000,000. It will eventually come down and converge to this equilibrium. And so in particular, we can answer the question we set out to answer. So if y of 0 equals 3, then the limit of y of t, what is the limit of y of t as t goes to infinity? You can see it in the picture, right? The limit, that's this one here, right? But it didn't matter whether I put 3 or whether I put 2.5 or whether I put 1.1. The limit is always going to be 4, as it will increase to this equilibrium solution, which is y equals 4. So the equilibrium solutions really sort of dictate the behavior of all the other solutions to autonomous differential equations. So it's really the key to studying autonomous differential equations is the equilibrium solutions. Okay, so before I finish this lecture, I just want to do one more quick example, just to kind of show the power of this idea. So here's another example. this will be something we've seen before, terminal velocity. So it'll be part 2. And we're not actually going to do anything new. I'm just going to show you how we could have just avoided that whole nasty calculation we did before in order to find a terminal velocity. Instead, we can use equilibrium solutions. So let's just recall what terminal velocity is. So if v of t is the velocity of a falling object, so velocity of a falling object, well, what we did is we wrote down a differential equation that v is going to satisfy. And that's because, okay, so how do we get a differential equation? Well, the net force was mg, the force due to gravity. We're saying the downward direction is positive, so let's have positive mg. And then we had a force due to air resistance opposing the motion. So we had some constant proportionality times v, gamma v. Okay, and that's because we were assuming the air resistance was proportional to the velocity, but in the opposite direction. Okay, this gamma we called the drag coefficient. Okay, and this is a differential equation. Why is it a differential equation? Because, well, Newton's second law tells us that when we have a force, that induces an acceleration. So we get m times dv dt is the acceleration, right? But I want to write it in terms of v, so that equals mg minus lambda v. So that was our differential equation for the falling object, assuming that the force due to air resistance is proportional to the velocity and not the square of the velocity. We said it could also be proportional to the square of the velocity in many cases. Okay, so let's, I'd like to write this in a slightly different form. Okay, so I'll divide by this m, so dv dt equals g minus gamma v over m. And then, just because it makes it easier, I'm going to try to just isolate the v. So I don't, or in other words, I don't want any coefficient on the v. So I'm going to pull this coefficient out. And so I just get, well, what do I get over here? This is now g times m, right, over gamma minus v. So all I'm doing is rewriting it, just because it makes it a little bit clearer to see what's going to be happening. Okay. Okay, so first of all, what is the equilibrium solution? Or solutions, maybe there are multiple ones. Equilibrium solution. Well, again, we set dv dt equal to 0. Right, so 0 is going to equal, this is just a constant. We can just divide by that. And so we just get 0 equals mg over gamma minus v. So v has to be mg over gamma. Okay. All right. So let's draw a, let's draw it up here actually. Here's v and here is t. Okay. And we have an equilibrium solution at mg over gamma. Okay, so the constant solution, v equals mg over gamma, is an equilibrium solution. Okay, is it the only one? Well, yes, because when we solved this, we got exactly one value of v, right? It wasn't like this one where we got multiple values. Here we got exactly one value of v. It's the only equilibrium solution. The next thing I would ask is it a stable or unstable equilibrium solution? Well, that's why I rewrote it in this form, just so it's easier to see what the sign of everything is. So what if I plug in a number for v that's greater than mg over gamma? You see what's going to happen here? I'm going to get a negative number here. And because these are always positive, dv dt is going to be negative. And so my solutions starting above mg over gamma will be decreasing. And if v is less than mg over gamma, this number here will be positive. Right? Subtracting a smaller number from a bigger one. And so because dv dt is positive, v of t, my solutions, will be increasing. And so here's a picture. Let's say I start at 0, right? I'm going to be increasing. Or I could be going like this. Or I could start at negative, right? I could start way down here. I'm moving in a completely opposite direction. But yeah, I still end up here, right? Because this is the only equilibrium solution. So it literally attracts all the other solutions. They all end up here. If I'm starting at a greater velocity than mg over gamma, I decrease my velocity until I'm going at exactly mg over gamma, or at least close to it. Right? And so what is the terminal velocity? Oh, of course it has to be mg over gamma. So that's the velocity that any object will eventually approach, because this is a stable equilibrium. Right? And notice that includes objects that are going faster than the terminal velocity. So terminal velocity isn't just some limit where you can't possibly ever go faster than it. You can go faster than it, right? For example, an object can be launched faster in terminal velocity, but then this is saying it will eventually decrease to the terminal velocity. So notice that we were able to answer this question without actually solving the differential equation. So it's a really powerful idea. And we also at least understand qualitatively what all the solutions are going to look like. So next time we're going to sort of take this concept to another level and yeah, see what equilibrium analysis can really do for us.